Hello class, today I'm going to do one simulation to cover boiling and condensation chapter. This is a little bit difficult for me because we don't have the enough knowledge about different numerical methods we use for multi-phase problems. So basically this homework is going to be just taste of multi-phase simulations, and if you were interested you need to study more and follow yourself about the details of these type of methods. I'm going to use VOF method or volume of fluid method. This method is exactly similar to the Navier-Stokes or finite volume method, and in addition to that, for Navier-Stokes formulas and energy formulas we need to solve to get the information we need. Volume of the fluid method has one extra item which is going to recognize the interface between two or three different fluids. So in this method we have extra calculation to find the fluid interface. So for example, this C is going to recognize the interface. When it's 1, it's fluid 1. When it's 0, it's fluid 2. There are many methods of the recognizing these methods, and which is too much details, and I'm not going to include in this homework. Okay, so let's see what is the geometry. For this homework, the geometry I'm going to use is this. As you can see, this is two circles at the top and bottom, and straight parts attaching those parts. This geometry has just fluid area, and I'm not simulating any solids, so it's not going to be a conjugate simulation. Only fluid simulation is going to be involved in this one. So let's see how I start drawing. First step was I draw this. Basically, I draw one circle, as you can see here, and also I draw this line, half a circle and two lines like this, and I swept this circle through this path. So I created this geometry. Then I asked SolidWorks to mirror from this surface, so it is going to be two surfaces, two geometries here. And next step, I said let's split from the center, because I want to have very hot surface at the bottom and cold surface at the top. So if I had a fluid inside this area, the hot area is going to generate, for example, it's going to be water. It's going to evaporate and boil, and steam is going to go upward here, and when it reaches to the cold side here, it's supposed to condensate and go back. And this is basically a heat pipe. So let's see what I did. So I split from the center. So now you can see I have two parts, lower part and upper part. Then I again split to have to use the half of this. So I split it using this line. And then I deleted that side. So I deleted the lower part to have just upper part. So my heat pipe is going to be like this. Then I save as an IGS file and import it into the Fluent. Let's open the mesh and see what type of mesh I applied. For multi-phase simulation, we need very refined mesh, and for that is why usually it takes long time to simulate and very computationally expensive. I did my best to increase the mesh quality, but still the mesh quality is not enough, and you may see some errors or unexpected results to some points which supposed to not to be there. And I'm going to mention those parts, but if the mesh quality was better, we could solve those problems. Okay, so as you can see, we have two parts: the green part, the upper part, cold part, and the lower part, hot part. Let's see if I had a connection. Yes, contact between the lower part and upper part, the red one and blue one, which is everything is excellent. Let's see what is the heater. Heater part is going to be this part. I selected the surface as a heater, and condenser is going to be top part, which is going to be cold. Then I selected symmetry as this layer, and you know this surface is going to be symmetric surface, and when we say symmetry, it means we don't have any heat flux. And let's see what is the mesh condition. It's not very good, and let me see how many mesh I have. 81,000 elements. It could be much better, but yeah, even this simulation took, I think, 5-6 hours to finish. So yeah, it's enough. Let's see what are the data I put. I included the maximum phase size as 0.001, and yeah, this is the mesh quality I have, and you can see the solid 1 is going to be upper part, and it is going to be air. Lower part, solid 2, is going to be water. When I apply this boundary, the heater part here, it's going to start boiling the water, and water steam, or the water steam is going to rise and reach this part, which is going to be cold, and condensate and go back. Okay, so let's go and open Fluent. Okay. Okay, now I have my geometry in the Fluent. Based on the x, y, z axis, you can see that my g, or gravity, is supposed to be negative y direction. You must include gravity, because gravity is going to show the direction of the water stream supposed to raise. If y negative is going to be our direction, the gravity direction, so streams are going to raise up in y direction. And simulation is going to be transient. Let's check the models. It is going to be multi-phase simulation, so we need to turn on the multi-phase models. I'm going to use volume of fluid, and for the number of Eulerian phases, you need to include 3 phases: one for air, one for liquid water, another for steam, and include implicit body force for this calculation. because we have temperature, you need to turn on energy equation too. And for viscous, this is not going to be laminar flow, it is going to be turbulent flow, and I selected K epsilon. And to improve the quality of the data close to the wall, I selected enhanced wall treatment and curvature correction, and also turned on thermal effect here. Okay, so we're done with the models. For the material, I selected fluent database and included water liquid and water vapor, and click this copy. Now after clicking that copy, you are going to see water vapor and water liquid is there. So you have 3 different fluids there. Okay, now cell zones. Cell zone number 1 is going to be later I'm going to show you this one. So before starting cell zone, let's go and assign phases. If we assign phases, everything would be okay. So setting of physics, I'm turning on this tab, and if you come here, you can see all the phases, and we have 3 phases here because I included 3 fluids there. The first one, if I double click, is going to be air. Primary phase is going to be air. You can select, for example, water as a liquid water as a primary phase. Primary phase is going to have more accuracy in the calculation. The secondary phase, I selected liquid water, and the other secondary phase, or the third one, is going to be water vapor, and I named it steam. So the first phase I named air, the second one water, the third one steam. Then we need to take care of interaction between the phases. When you turn on, here it is the number of mass transfer mechanism is 0. You need to increase to 1, and you need to say there's a evaporation and condensation between water and steam. So from here you can select the type of mechanism of mass transfer we have between water and steam. We also need to include surface tension information. Between water and air, I selected as a constant number. You can say any type of formula, and if it's variable, I selected constant, which is the easiest, and the value for surface tension between water and air is 0.072. I also included it for steam and water. Let me check. Yeah, for steam and air, also the same surface tension. That's it. Let me check once more. And here you can add temperature. I don't know why this is not working. Yeah, so you click edit, and it is going to say what is the evaporation condensation temperature. It's going to be 100 degree. So 100 degree is going to be 373. But I'm selecting 308, which is lower, because we are going to have a little bit lower pressure inside our heat pipe. So having lower pressure inside heat pipe is going to decrease boiling or evaporation temperature. So 308 is because of that. And I'm going to show you where to include that pressure. Okay, now we finished this part. Now let's consider operation condition. For the operation condition, now operating pressure for this heat pipe, instead of being 1 atmosphere, it is going to be 4,000 Pascal. And this is absolute pressure. So we have low pressure inside this heat pipe, which is going to decrease the temperature, boiling temperature, evaporation temperature of the water. Okay. Let me check. Okay, this is okay. Let's open boundary conditions. For the condenser, which is the top part, we are going to have constant temperature, and it's a room temperature 298. Because I didn't simulate any solid here, I'm going to have a wall thickness 0.5 for the heat pipe wall thickness. Okay, so condenser temperature is going to be 298 degree, and the wall thickness is going to be 0.0005 meter, which is half of a millimeter. For the heater part, the temperature of the hot part is going to be 393, and again same wall thickness is given here. Symmetry components are going to be taken care of automatically, because you know that ANSYS, the default boundary condition for the any wall is zero heat flux, and zero heat flux is the best case for us when we have symmetry surface. Let's see what is the method I selected. Simple. These are the all default schemes and methods, and I didn't change them. Then I went and initialized it, and after initializing you need to patch it. Let's initialize, because if I don't initialize, I can't show you the patching part. So if I initialize it, now you can see the patch part. To patch this, you know, patch is like an initial condition. So I would like to have water at the lower part and air at and steam nowhere, because it is going to be starting point. So phase is going to be water, and volume fraction of the water for solid number 2 is supposed to be 1, and I patch it. Then I select steam, and volume fraction for steam supposed to be 0 for upper part and lower part both, and then I patch that one. So this is going to be initial condition. Basically, at the upper part it's going to be air, lower part water with no temperature. Then temperature, the hot surface here is going to start, and water is going to start boiling, steam is going to rise, and when it goes up, the cold surface is going to condense the steam, and it is going to go back, and this heat transfer mechanism is going to continue. Then calculation activities. I open this, CFD post compatible, selected all of these, and I added volume fraction. For the air, volume fraction for the water and volume fraction for the steam, because I want to know what is the volume fraction of a steam when it moves in the heat pipe, and also the regular results like a temperature, velocity, and pressure. And you need to specify the address, so I send it to one of my folders to save, and the frequency was every 20 time step it is going to save the data. And then I start running calculation. The time step actually was 0.0001, and then I decided to make it variable because it was very difficult to converge, and the number of time steps you need to have very large time step to see. And I didn't change the maximum iteration, and it's 20. Then the calculation is going to start. It's a little bit time consuming, and let's see results. I already solved this, and let's see the results. So to see the results, you're going to create a plan, and z is going to be 0. So if z is going to be 0, this plan is going to be at that surface which we want to see what's happening. Okay, now I have my plan. For the color, instead of having constant color with gray, I'm going to say make the color variable. What is the variable? I want to see the color based on steam volume fraction. If I apply, now you are going to see what is happening inside. So this is my steam fraction, volume fraction. After how many? It's almost 1.177 seconds. So it's not that much simulation. It took me several hours to finish. So if I start from beginning, you can see how this heat pipe is working. Oh, no. At the beginning, nothing. This is a error I have because of the large mesh, so just neglect this one. Now you can see the heater part is going to increase the red. Red is 100% steam. So steam is created, and after creation, they're moving upward. As you can see, they're going up, up, and even we have smaller bubbles of steam there. The amount of steam is not enough accumulated here. Now, when it gets bigger, it have enough force to move upward. Let's see. Now, okay, from right side, we enter the cold side of the heat pipe. So you can see that steam is very hot. We have steam, but it doesn't go up higher than that because we have a cold area here, and we have a condensation here, and the steam condenses to the water and goes back to our heat pipes, liquid part. Amount of steam increases, and we have this circulation from evaporation here. We have accumulation of the steam, and then condensation happens. You can clearly see this condensation happening, and we have upward and downward flow inside this heat pipe. Still, we have this boiling and evaporation mechanism at the hot part. At the cold part, we don't have that much steam, and they are very rare, and if there are, gradually they are condensing and coming back to the water portion. Okay, so this is the one. Let me show you the video I created for this one. Why I couldn't maximize? Okay, now you can see it goes up, and you can clearly see we have condensation here happening, and the steam condenses and comes back, and the drops of the steam converts to the water, and they are dropping. Okay, what else? You can check the temperature. This is the temperature, and do the same. And I also created a video for the temperature. Not this one. This is the one, yes. Again, you can see that downward flow around here. If I simulate for longer time, instead of 1 second, for example, 2-3 seconds, you are going to see we have more steam at the higher parts, this part, and condensation happening at the this level. Okay. Okay, this is enough. I hope you enjoyed this one, and I know there are some parts I didn't explain because this topic is out of our subject scope, and we just need to learn the basics about evaporation and condensation. Okay, see you next time.